Hello everybody, welcome back to our virtual fluid mechanics labs. This is experiment number 3, and it's a very interesting experiment because it's about flow in pipes.
So pipes are some of the most prevalent and some of the most important applications of fluid mechanics, right? We find piping everywhere in all different forms, whether that's circulation of gases, of liquids, and at many different scales.
Right. Well, speaking of scales, we have pipe networks that transport oil and gas throughout our nation with hundreds and hundreds of miles of pipe, different diameters, different age, pretty complex network. And those networks are actually also reflected in our body. A lot of what we learn in terms of flow in pipes applies to how blood moves through our veins and arteries.
That's right. So the particular experiment we're going to be showing you today has a little bit of a historical background here at IIHR and the University of Iowa. It was originally invented by Hunter Rouse, who was a director of IIHR during the 1940s, and who really revolutionized some of the teaching that happened here as well as across the United States. He's affectionately known as the father of hydraulics, and the experiment that you'll be seeing was actually designed and constructed by him and is still in use today.
Yeah, that experiment got moved from our old annex lab in IIHR to these new facilities at the College of Engineering, and along with the moving, there was a significant revamping of the experiment. As you will see during the experiment execution, the system was fitted with electronic pressure transducers that make all the measurements more precise. We also added a new mechanism to measure the flow rates. In the original experiment, there were some Venturi measurements that were being done, but we're not going to be using them in this experiment.
So we'll be spending a bit more time walking you through the different elements of the experiment live rather than showing them all to you here. But this schematic has a few alterations that can be made to describe more accurately what we're looking at today. We're going to be focusing on this 2-inch smooth pipe, this 2-inch rough pipe, and we'll be neglecting the treatment of the return pipes, leaving that for future work that's going to be dealing with instrumentation as well as minor losses. Now, a few of the other elements we won't be discussing include the electronic data acquisition systems, because we'll be collecting our measurements, although digitally, manually.
Yeah, so let's start thinking about what happens to flow and to the energy contained in the flow as it moves through a pipe. So in this case, we have a particular pipe where flow is moving from left to right. And because the geometry of the pipe is not changing, the velocity profile inside the pipe, we're going to assume that it's constant. So that means the form of energy that expresses as kinetic energy is going to remain constant throughout the pipe.
And attached to this pipe are 2 piezometers, which you might remember from our experiment with the sluice gate, which give an indication of the pressure head inside of a flow. And what you might notice is that the upstream piezometer has a higher water level than that of the low stream. The reason here is what we know as head loss. And head loss is a way we describe the energy lost when fluid moves through a pipe, with those losses usually occurring due to thermal losses and friction.
Right. So we're going to be using this experimental setup to determine the magnitude of the head losses that happen inside pipes that are relatively smooth and pipes that are relatively rough. So we have those two setups, and we're going to be using our experiment to determine how quickly energy dissipates in these two types of systems. The other big advantage of the experiment that we will be conducting is that it lends very well itself to dimensional analysis. So everything that we learn on circulating air through these pipes will be applicable to the movement of other fluids. liquids like oil or water or any other type of liquid.
That's right. With the modest experiment behind us, which involves air flowing through a 2-inch pipe, we can represent correctly the way that flow behaves moving through a whole range of different pipes using different fluids. And this is what makes dimensional analysis so powerful.
The instruments we're going to be using in the setup are a Venturi, which are not going to operate, but I would like you to describe. And the second is a Pitot tube, which is an instrument that we will use to determine velocities of flow of air.
Now, as Ricardo mentioned, the Venturi meter isn't being used in this experiment, but it is a very important instrument used in many pipe flows. And the Venturi meter and the Pitot probe both share common lineage. That is, they both use the Bernoulli equation in order to infer what the flow velocity is. In the case of a Venturi meter, there's a contraction where the flow speeds up, and with that increase in speed comes a reduction in pressure. So by measuring the difference in pressure between the base flow and this constricted flow, we can find the velocity of the flow through that section. The Venturi, or the Pitot probe, very similarly, uses the Bernoulli equation, but in a slightly different way. Rather than by using a contraction of an internal flow, it uses what's known as a stagnation tube that stops the incoming flow of an external flow, and in that tube measures what's known as the stagnation pressure, which is then compared to a static pressure measured along the side of the probe to get the velocity head from which the velocity can be calculated. Pitot probes are found, as in this photo, on many airplanes. In fact, if you are ever able to fly again after this pandemic, take a look to your left as you board the airplane, and you may see one of these no step signs with this little L-shaped instrument sticking out of the fuselage, and you'll know that that's a Pitot probe used to measure wind speed.
So we can use some of our theoretical formulations to be able to determine what is happening to the flow and how we calculate these head laws. In particular, we know that in laminar regimes and pipes that are very smooth, we can calculate the difference in pressure as a function of variables of the fluid alone, the velocity of the fluid, the viscosity, and the diameter of the tube. This is different when we have highly turbulent flows or high roughness material, where the relative roughness of the pipe becomes an important variable in determining the head loss as you move through the pipe.
Right. It makes sense intuitively that pipes that are rougher are going to experience more energy loss, right? It's one of the reasons that high-performance vehicles have very smooth and high-finish surfaces or high-gloss surfaces, is to minimize friction. And we'll see through the measurements in this lab that the product of added roughness in the pipe is to induce extra tortuosity or turbulence in the flow that creates a lot of intermolecular friction between the different flow particles or fluid particles, as well as between the flow and the walls of the pipe. All of this amounting to more heat and therefore more energy loss, which means that the pressure drop between point 2 and point 1 will be increased.
So that brings us to our data reduction equations. So we're going to be using two equations of significant importance. First, the equation for the friction factor, or the Darcy-Weisbach friction factor, which relates that our energy loss, that change of pressure, the diameter of the pipe, the flow in the pipe, and the length that is traversed through a coefficient that will tell you how much energy is dissipating in the system.
That's right, and it's worth noting that this friction factor is a dimensionless quantity, meaning it has no dimensions or units attached to it. This is one of the things that makes it so powerful in the dimensional analysis.
The second number we're going to be considering here is the Reynolds number. So Reynolds number is a quantity that allows us to express the relationship between viscous forces in the fluid to inertial forces in the fluid. And we're going to see how the friction factor is going to be dependent on that non-dimensional number. So we have a non-dimensional relationship that we're going to be exploring here.
That's right. And something to keep your eye on is that you'll notice that both in the expression on the last slide for F, as well as in our expression for the Reynolds number, we have the volumetric flow rate showing up, Q. Ordinarily, this is a quantity we'd get using that Venturi meter that we have installed in the pipe network. However, we're going to be taking a slightly different approach using the pitot probe and the measured velocity distribution to actually manually calculate the volumetric flow rate leaving each pipe.
Yeah, I think that's an exciting part of this experiment.
It is. So it allows us to compare our results to classical results like those shown here, which are attributed to Schlichting in his work on boundary layers. And it allows us to get some practice in how we can turn point measurements of velocities into approximated integrals.
Yep, and that's going to come at a cost that the propagation of uncertainties through this more complex equation is also going to add another layer of uncertainty to our measures. Just to give you an idea of our experimental setup, we're going to have two pipes that, as we said, they have approximately the same diameter in millimeters here, but the internal surface changes quite a bit. So here, the roughness that we measure for the smooth pipe is 0.025, and the roughness for our rough pipe is going to be about two times higher.
So it's also worth noting that these roughness values are a little bit hard to determine. These are what are known as representative roughness values and are usually taken to be either the average or the RMS height of individual roughness elements along the wall of the pipe, measured using what's known as a profilometer.
We will use the results of our experiment to compare to well-known and well-established relationships between these factors, which are all encoded into the very famous Moody diagram, which gives us a relationship between the friction coefficient, the Reynolds number, and the relative roughness for a pipe.
That's right. The Moody diagram is one of the most important tools in anyone doing pipe design or water distribution planning, because it allows you to, by calculating the Reynolds number, knowing the roughness of the pipe, or those two quantities alone, you can find what the friction factor is, which can then be turned into the pressure drop per length of pipe.
So let's go and perform an experiment, and let's see how good we can approximate our values to these standard measurements on the Moody diagram. So let's start by describing our experimental setup. So what we have here is a pump that is going to be pushing air through the system. That air is going to fill up this reservoir with enough pressure that is going to force air down these pipes.
So these three horizontal pipes behind me vary in two important ways. You'll remember that the pressure drop in a pipe depends upon the diameter as well as the surface roughness of the interior of that pipe. So the ones we'll be focusing on today are the top and the bottom pipes, both of which have an inside diameter of about 2 inches. But the top pipe is very smooth inside, whereas the bottom pipe has been artificially roughened. And we're going to use that information to help quantify the differences in energy loss as air flows through each of these two pipes.
So we are now at the other end of the experimental setup, and we're going to describe the instrumentation we're going to be using to make measurements. So first,
so the principal piece of instrumentation we want to show you is the differential pressure transducer here, which is equipped with a digital display. Now, a differential pressure transducer tells you the pressure on a high pressure leg relative to that on a low pressure leg. And the digital display, you may notice, is providing a reading in feet of water. Now, if you recall our lessons on manometry, you'll remember that a manometer is a device that allows you to visualize a pressure difference as a water elevation. By increasing the pressure on one leg, you induce a change in the relative water column heights that can be measured in feet, which is precisely what's being read out on this display. So we need to be mindful that the numbers we get from this display have to be converted to true pressures using the principles of hydrostatics.
So our device here uses electronic pressure transducers, and we have set it up so that we can change the locations of where we measure pressure, so we can connect the low end to one part of the pipe.
And the high pressure end can be connected to a tap that is upstream.
So when air is flowing, the pressure transducer is going to be giving us a reading of the difference in pressure at this point in the pipe and the pressure in this point in the pipe.
So at the downstream end of our experiment, you'll notice that we have an array of valves which can be opened and closed to shut off or open individual pipes to direct the flow through any choice of supply or return pipes. Also, on the two supply pipes that we'll be considering, the smooth and the rough 2-inch pipes, we have these yellow housings, each of which contain a pitot probe. Now, the pitot probe is a device we can use to measure the flow velocity through the differences between two pressures. This lower line connects to a brass tube, which is then directed into the incoming flow to measure what's known as the stagnation pressure. On the bottom of the box, we have a second tap, which measures the ambient pressure inside of the box, or what's known as the static pressure. By using the same differential pressure transducer we used in the pipes, connecting the high pressure leg to the stagnation pressure tap and the low pressure leg to the static pressure tap, we'll be able to obtain the difference between those two pressures, which is then proportional to the velocity squared. Each of these pitot probes is equipped with a traverse that allows us to move it across the pipe's cross-section, and therefore allows us to measure the velocity at different points along the pipe's radius. We'll use this functionality to obtain a velocity distribution inside of the pipe, which will then integrate to come up with the total flow rate.
Throughout the experiment, we will be keeping track of the temperature in the room and the temperature of the air that is moving inside the pipes. So let's describe the measurements that we will be making during the experiment. We will use this pressure transducer with one end open to the atmosphere to measure gauge pressure at 4 points along the pipes. We'll measure pressures here. Point number 1, point number 2, point number 3, and finally point number 4. We expect the flow to be fully developed by the time it reaches points 3 and 4.
Following the measurement of the pressure drop along the length of the pipe, we'll be moving a little bit further down to measure the velocity profile across the pipe using our pitot probe. So, with our second differential pressure transducer, we'll attach the high pressure leg to the stagnation tube and the low pressure leg to the static pressure tube. We will then use the traverse that is equipped with a set of calipers to indicate distance to move the tube to different radial positions across the pipe's width, which will allow us to measure the velocity profile across the pipe, which will then later integrate to get the flow rate. After this measurement is completed, we will close the top valve and open the bottom valve to redirect flow through the rough pipe and repeat all of those measurements again using the roughened pipe. Our measurements are not perfect, so we need some way of assessing the repeatability or the precision error that may be present in our experiment. To accomplish this, Ricardo will be measuring the pressures, static pressures at taps 3 and 4. Ten times each to give us a sufficiently large statistical sample. I'll then be moving the pitot probe to the position nearest the wall and obtaining 10 independent measurements at the velocity so that we can establish the precision limit of our velocity measurements within the pipe.
So let's start doing our measurements. We start measuring pressure at point 1. We'll wait for the pressure transducer to stabilize. We move to point 2. So we get our measurement. We move now to point 3. So we got a measurement here. Finally, we move to point 4. We have our measurement. So we're going to repeat these last two measurements. That's our measurement. That's our measurement. And we want to do this 10 times.
Okay, now we're going to be measuring the velocity profile across the pipe using our pitot probe. We have our calipers zeroed with the stagnation probe along the center line of the pipe. So moving it down, we'll get negative values from center line, and moving it up, we'll get positive values. We're going to be measuring at radial distances from the center line of 0, 5, 10, 15, 20, 23, and 24 millimeters, which will take us just up to the edge of the interior surface of the pipe. So for the first measurement, we'll put this at 5 millimeters below the center line. And we have our high pressure leg connected to stagnation and our low pressure leg connected to static pressure, giving us a pressure difference of approximately 0.892 feet of water. Now you'll notice some fluctuation present in our measurement here. This is physical, and this is one of the reasons we take repeated measurements to quantify uncertainty. Moving to the next measurement location of 10 millimeters. We obtain 0.83 feet of water. At 15 millimeters, we obtain 0.753. At 20 millimeters, 0.642. Now you'll notice that this pressure is falling as I move away from the center line of the pipe. This is an indication that the velocity is decreasing towards the walls of the pipe, describing our classic velocity distribution inside of a circular pipe. Moving to 23, we have 0.52 feet of water, and at 24, which is just off the edge of the interior surface of the pipe, 0.457 approximately. Moving back to center line to obtain our center line measurement at 0. We get 0.908 feet of water. Now the repeated measurements are going to be acquired at the edge of the pipe, or at 24 millimeters, where we will move the probe into place, obtain a measurement, move it away, replace the probe, obtain another measurement, for a total of 10 replicated measurements. So at 24 millimeters, .456. Resetting the probe's position, we expect that there may be some variability in where we place the probe, as well as in the actual process of the fluid moving through the pipe that would cause us to get a slightly different measurement, 0.445. So we'll repeat this process a total of 10 times to build up a statistical sample that we can use to infer the precision limit of our velocity measurements. 0.440.
So let's repeat our temperature measurements. So you can see the temperature in the room hasn't changed. The temperature inside of the air, inside the pipe, has increased. So now we're going to repeat the measurements that we did on our smooth pipe in our rough pipe. So we're going to use our pressure transducer to measure pressures at 0.3. That's our measurement. Then you can repeat that. And you will notice that we lose pressure faster on the rough pipe than we do on the smooth pipe.
So now that we have flow moving through the rough pipe, we need to duplicate our set of velocity measurements with the flow coming out of this other pipe. So we have another pitot-static probe, again with a set of calipers zeroed at the center line of the pipe, allowing us to measure the difference between the stagnation and static pressure at different radial positions. As with the smooth pipe, we'll measure those at positions of 0, 5, 10, 15, 20, 23, and 24 millimeters from center line. We'll go ahead and do this both below and above the center line, which will allow us then to get a fully defined picture of what the velocity profile across the pipe's diameter looks like. As with the smooth pipe, we'll then conduct 10 repeated measurements with the probe located at 24 millimeters from center line to assess our precision limit.
So this is our third measurement of temperature. So as you can see, the temperature in the room has not changed. And now the temperature of the air moving into the system is 31.7 degrees centigrade. Okay, so we're done with our measurements on the pipe experiment. So we measure differences in pressure, and we measure pressures using our pressure transducers, and we measure differences between the stagnation pressure and the static pressure to be able to determine velocities there.
That's right. So we need to take another walk through how we turn those measured data into the volumetric flow rates, the friction factors, and the Reynolds numbers that we're interested in at the end of the day.
So the friction factor, we're going to use the repeated measurements that we made along the pipe to determine differences in pressure at the different locations.
So you'll recall that when Ricardo was measuring the static pressure at the 4 taps along each of the pipes, he recorded those independently. One of your options for the friction factor is to, for example, calculate the friction factor between taps 1 and 2, as written here, between taps 2 and 3, and between taps 3 and 4. And please remember that taps 3 and 4 were each measured 10 times, meaning we'll have 10 independent estimates of the friction factor between 3 and 4, which we'll talk a little bit more about in a moment.
Yep. So the measurements of velocity, you use the Pitot probe to estimate velocities at different depths or at different radial longitudes along the pipe, and you used the difference between the 2 pressures.
Correct. We had one side of the differential pressure transducer plugged into the static pressure probe, and the other, into the stagnation pressure probe, and the other plugged into the static pressure probe. The difference between thus giving us the velocity, or something that's proportional to the square of the velocity.
So once again, we find ourselves with our data reduction equations, which we can use to determine the precision that we can, with which we can estimate our friction factor and our velocities in the pipe, and they will depend on our ability to measure precisely pressures in different points, or like you indicated, the difference between 2 pressures in different locations. So in the case of the velocity inside in the pipe at any location, we have a function that is going to depend on gravity, the density of the fluid, and it's going to depend on this difference in pressures. Here they are expressed as elevation or water heads.
Correct. So this is given for a classic version of this experiment in this equation here. So we need to be careful how we apply this. For example, in the original version of the experiment, the stagnation pressure and the static pressure were measured individually, whereas when we performed it, we chose to measure the quantity P or Z, stag, minus P static, as a single measurement, right? So we'll need to replace some of the terms in our propagation equation to reflect that these are no longer 2 random variables. This will be accomplished by crossing out one of their contributions and simply replacing the remainder with our new definition of our random variable. The other thing we should be conscious of is that we have 2 densities here, one of the air flowing through the pipe and the second of water. Now the reason that water is included in there is because of the use of manometers, right? Water is acting as our gauge fluid, and uncertainty in the density of the gauge fluid will mean that you're less precise in how you convert the manometer head into a pressure. Our water is digital, right? We're using digital pressure transducers. So we don't need to worry about this, and we can eliminate this from our uncertainty considerations entirely.
Yep. So, but we still have 2 sources of uncertainty associated to this experiment. We have an uncertainty associated to our precision limit, and an uncertainty associated to the bias limit, because the instruments we have a finite resolution, and a precision limit, because our measurements, if you remember during the performance of the experiments, they vary quite a bit during the experiment. So there is a random component in the measurement of those.
That's right. So, as in the past, we're going to approach these 2 separately. The bias limit is going to be dictated by the measurement resolution of our instruments, meaning the pressure head indicated by our differential pressure transducers, which comes out to be about 0.01 feet, as well as the density of the air, which comes down to uncertainty in the temperature more than anything else. Once we know these elemental bias limits, we use this expression to propagate them into the uncertainty in the velocity.
And I'm going to show you here the calculation for the the coefficients of propagation of uncertainty for the case in which the two pressures were measured independently. So we'll have to rework out the uncertainty propagation when the difference is the variable at hand.
Before you go on to the next slide, though, we need to mention that the precision limit is not treated quite the same way. You remember that when we did the sphere drop experiment, we decided it was easier to look at the scatter in the reduced data rather than trying to propagate the elemental precision uncertainties through our data reduction equations. The same thing applies here. You may recall that when I was using the Pitot probe to scan the velocity distribution across the pipe, I repeated the measurement near the wall a number of times, 10 in total. So we have 10 measurements of the velocity, which we can use to calculate the sample standard deviation, our coverage factor, which will be equal to 2 for a 95% confidence interval, and then over the square root of the number of samples, which is in this case is equal to 10.
So these are the reduction coefficients. They are just simply the derivative of our variable of interest, in this case the velocity, as a function of the variable of, that we're concerned with, or the source of uncertainty, which would be the pressure. So in this case, there are two equations. If we were going to take the difference between the equations, then that would change that form of the coefficient.
And the change will simply come in the form of no longer worrying about one of these at all. You remember we crossed out one of the terms in the propagation equation before. We can do that again here and simply treat this quantity itself as our random variable, which means that this is now our sensitivity coefficient for the stagnation minus the static elevation.
Mm-hmm. So that there's no limitation on how you define your variables in there. The second variable of interest was the friction factor. This one, again, depends on several variables. Depends on the diameter of the pipe, the length of the pipe, the flow that is moving through the system, again, the densities of air and the tap water that we said we were going to eliminate. And it depends on the sensitivity or on the water heads that we measure. In the case of friction factors, I did measure gauge pressures. So we use independent measurements of the tap 3 and tap 4 to determine this friction factor.
That's right. And so the propagation of bias uncertainty is exactly what's shown here, where we need to be mindful of the contribution of the elemental uncertainties in the individual gauge pressure heads, length, diameter of the pipe, etc.
So if we use a data reduction equation, these sensitivity coefficients come down to these two equations that we can use then to propagate our uncertainty on our measurements to our estimated variable.
That's right. And remember, once again, the precision limit is not being calculated through propagation. It's being calculated from the scatter in the friction factor. Remember that when Ricardo was conducting the pressure drop measurements along the length of the pipe, he plugged into taps 3 and 4 10 times each, which will give you 10 pressure drops, which you can non-dimensionalize into friction factors. So you have a whole sample of F values that you can turn into a precision limit.
Yep. The result that comes out of this experiment are twofold. One of them is going to give us the distribution of velocities in the along the pipe. I think the way you made the measurements, you assumed that these measurements were symmetric, so you were only making measurements from the center of the pipe to the higher end. Is that correct?
That's correct. I measured from the center line toward one wall. The execution of this experiment depends upon the person who is running the lab as well as the experimenter themselves. You may find yourself with data that includes measurements across the entire diameter or simply only from the center line out to the wall. In either case, you should plot your data on top of this sample data from Schlichting, which has been non-dimensionalized by the maximum or center line velocity. And you should have something that fairly closely matches the Schlichting data, especially when you add the uncertainty bars that you calculated using the steps from a few slides ago.
So that uncertainty in our measurements of velocities are going to transform into, propagate into uncertainties on our estimation of flow, which then will translate into uncertainties on a Reynolds number, and then can be compared to our estimates of the friction factor. So in the end, out of this experiment, what you're going to get are two specific estimates of friction factor for a particular Reynolds number and two different roughness of the pipes. Hopefully, those results will match very well with our Moody diagram.
So things to remember: careful bookkeeping in your bias limits. Make sure that you collect repeated data that you can use to estimate the precision limits. Combine those into total uncertainties, and remember to include those on any plots that are used to compare to benchmark data.
And that marks the end of this experiment. I hope that all of these experiments that we did are going to be useful for you, and we are going to be giving you some data that you can play with and some calculations for you to do associated to that.
If you have more questions about this, please let Professor Mantilla or myself know, and we'll be happy to help out. In the meantime, keep an eye out for any additional information on uncertainty analysis, as well as sample data from this and the other labs.
All right, everybody, stay safe. Thank you.